and open it, wouldn't it look like this, basically? Right, more triangles, but you get the idea. How are we doing so far? Is that okay? Do the same thing with the bottom. In fact, real quick, what is this length here? I made a big deal of it a second ago, and you see why now. Didn't I pick this up? Didn't I pick this up and open it?
It's pi r.
Yes, is that pi r?
Yeah.
Right? I picked it up and opened it. That's pi r. This is pi r. How tall is this about?
We don't have a radius.
R. Now, if you do the same thing with the bottom one and fit it in, if you do the same thing with the bottom one, cut it, and then fit them in, so close the mouth, right? Fills it in, basically.
Yes.
And of course, the more triangles you make, the more perfectly it'll fit it in. But what shape have I basically made?
Rectangle.
And really, it's going to be a little curvy, but it's still going to be basically a rectangle. The smaller my triangles, the more perfect the rectangle gets. And we know what a rectangle formula is. What's the area of this rectangle? Careful. Careful. Isn't it length times width? Pi r times r. What's pi r times r? Pi r squared, and that hopefully sounds familiar. So what do? When you have a shape you don't know, you cut it into shapes you know, and then put them back together. So that's cool. You've seen that before?
Well, I would look more on the parallelogram.
Oh, for the parallelogram.
Yes.
But isn't that cool?
Yeah.
Like when we did it, the
Oh, they did? They're better. Oh, I see. Okay. I was about to say they're better than me. Someday I'll actually get the
Well,
construction.
it's our
paper.
project, we gotta figure it out.
Oh, okay, okay. That's kind of cool. You can imagine it. If you have decent spatial region, you can imagine just opening it up and then fitting the bottom one in there. I'm trying to make a shape that I know out of the area. Because, of course, cutting and opening is not going to change the area, will it? Only if I cut it part off, chip a tooth. But I haven't chipped a tooth. The whole area is still there. So it's still the same area as it would be. How would I have to do that if I couldn't do it like this? I'd have to use calculus. Oh, shit. So this is better, right? So that's kind of cool. So now there's an area formula that we need. Pi r squared for a circle. Okay. Stay with me now. Let's see what we get. So we've done triangle, square, rectangle, parallelogram, trapezoid, and circles. Let's take a step back and talk about Pythagorean, and then I'm going to let you try a couple out of this homework to see what they're going to look like. Right? The Pythagoras actually had a group of followers that did a lot of the work for him. He kind of was the supervisor, which if you ever learn about the history, you start to question a little bit. He's still an important person, but he did less of the work than you might think. So he's got his name on it, but how much of the work did he do? Well, we don't know. But anyway, he gets the credit. How many proofs of the Pythagorean theorem are there? Does anybody know?
3, 4, 5.
Hundreds of proofs. In fact, one of our presidents, I think it was Teddy Roosevelt, one of his hobbies was to develop other proofs of the Pythagorean theorem, which is like, normally go, geek, but you know. It's interesting to hear that one of our presidents is actually interested in like Pythagorean theorem proofs, which is something you don't hear. One of the most, this is not a proof, but I love this visual and this is going to help you remember the formula. Some of you guys probably already know it. Maybe. Okay. Which side has got to be the one I call C? That's the only important thing. The bigger one, because if you remember the formula, the other two go to make it, right? So obviously C must be the biggest one, which is called the hypotenuse, the one across from the biggest angle. Angle opens the most, of course that side must be the longest then, right? So this I'll call C. You can call either one of these A or B, whatever you want to call it, it doesn't matter. They're interchangeable. Now here's the cool thing, now watch. If I draw off the edge of A here, if I draw a square, just because I want to. Does this look familiar or?
No, it's just.
Oh yeah, it looks like.
What's the area of this? A squared, right? So the area of this is A squared. If I draw a square off of this, what's the area of this? If I draw a square off of this, of course my square is a little crooked, but I'll.
Looks like SpongeBob.
So if you took this area,
Yeah, I don't see.
Not quite a square there, but
It's okay. Screw that. I know it's not square. If you took this area, and add them together, it's going to equal that area. It's a really nice visual. I guess some of you guys, I'm a little tiny bit OCD. So let me see. All right, that's a better square. Still not perfect at all. You guys understand what I'm saying?
Yeah.
It's not a proof, but it's interesting. It kind of makes it this square plus that square equals that square. So because the biggest mistake I see is people just say A plus B equals C.
A squared.
That doesn't make any damn bit of sense. A plus B can't be C because they're not lying in the same direction, are they? If you add this to this, there's no way it can equal this length because they'd have to be lying in the same. Here, A plus B would equal C. There's no way that works. But the squares, think about that in your head. Keep this visual in your head, squares added together. So A squared plus B squared equals C squared. So when is that going to be useful? Well, I'll tell you this: if you have anybody taken the SAT yet, or like any standardized test, or anybody going to take it? No, haven't taken it yet, or all right. They love on standardized tests. They love this kind of problem. They always have triangle problems show up somewhere. They love that kind of thing. If you're going to go into teaching, you have to take like what's it called, a TEAS test. Anybody think about that? There's a certain test, another standardized test. They love to put little triangle problems on there somewhere. So here's the interesting thing. What if I had somebody, don't yell it out if you already know this. And I want to know the area of that triangle. Why is that a hard question the way it's given to me? I don't have the base. Now if you say, well, I want to use 5 as the base, okay, so I need this height, which is now even worse, right? Because the height has got to be perpendicular to the base. So I want to use this as the height. So I have to use this as the base, don't I? And what the hell is it? I don't know. But I can use what? Obviously the thing we just talked about. Why can I use Pythagorean theorem? It only works for what kind of triangles? Right triangles. Right? There's a bigger, uglier equation that works for any triangle, but that's a nice little equation only for right triangles. Right? So what can I set up here? Let's call this A, just for the formula. What's this side going to be? C. And B is the one I don't know, right? So how can you say this then? So A squared plus B squared equals C squared. So 9, 3 squared, plus something squared equals 25. I love it.
Subtract 9.
B squared equals 16, so B equals 4. Careful now. So B is 4. Anybody know the 3, 4, 5 triangle?
Yeah.
Can you imagine that? It should surprise you when you get a triangle where the side comes out to a whole number. Because what do we have to do from this step to this step, really?
Take the square root.
Square roots. And square roots of most numbers are disgusting.
Yeah.
Right? If I would have made this 6, this would have been 36 minus 9. 27. Square root of 27 is not pretty. Right? So there are 3, 4, 5 triangle. There's also a 5, 12, 13 triangle. There's also a 7, 24, 25 triangle. Blah, blah, blah. There's a few of these triplets in existence. Right?
Yeah, my teachers, they made us try to memorize no suppose.
Really? Cool.
Yeah.
They're called, I can't remember if they're called Euler triplets or Gaussian. I can't remember. But anyway, they're triplets that work for the sides of a right triangle.
Yeah,
Okay.
ones that are whole numbers.
Let me ask you this. If I had a right triangle, this was 6 and this is 10, what do you think that last side's got to be? You have to do any work. Careful. Why 8?
It's gotta be.
Halfway between both of those.
I love it. But you must be able to explain yourself, though. So it is 8.
So it's like
It's
2.
probably 2.
Yeah, halfway in between.
What do you mean 2 and 2?
Like,
What did I do to that triangle to make that triangle? I just,
multiply
I
6.
doubled the whole triangle, didn't I? So if that's 3 and 5, if that's 6 and 10, this has got to be based on 4. So it's twice 4 is 8. How we doing? That's where the 3, 4, 5, or 5, 12, 13, that's where those come in handy, because if you see a triangle like this is 10 and this is 26, And you just, if you know 5, 12, 13, isn't this twice 5 and that's twice 13? So this has got to be twice 12, 24. Right? That's a shortcut Pythagorean theorem. Shortcut. In general, if I just make a triangle up out of nowhere, 4 and 7, this side is going to be disgusting. Right? It's going to be 7 squared, 49 minus 4 squared, 16. 49 minus 16 is 33. Square root of 33. Right? But there are a few that come out to nice whole numbers. How much of that do you really have to know for this class? Nothing. You just have to know this, really. But all this other stuff is just offshoots of this. Little problems that are easier to do. You don't always have to use this formula. If you have a nice triangle, 3, 4, 5 triangle. Okay, so let me give you guys a couple to try out of the homework. Just give you a feel for what it's going to be like. Page 546. Number, let's see, number R. Oh, here we go, number 6, 10,
Do we have to draw the triangles?
What's
Like
up?
to show our work, do we have to draw the triangles?
You don't have to draw the triangle now. Ooh, I like that one. See what you think about 28.
You're torturing us, aren't you?
I'm a math teacher, that's my job. I'm
Unfortunately for you,
that's supposed to say.
Unfortunately for me, I don't have to listen.
Alright.
It's really good hanging out.
It's raining.
I never.
And you guys, please, my day, I had to walk uphill both ways. That's not. Bless you. 10. So this wants area and perimeter. Oh, let's see. Oh, I had that. 28. 28. That looks like a magnet or something. So at the area that's shaded, so that's 5 inches. That's 10 inches. Obviously, mine is not to scale. So it sort of looks like the Loch Ness Monster. No. All right. Oh, interesting.
Yeah.
Be careful about units.
Yeah, I was gonna go. Just either gonna convert either or.
In this case, I'd rather, notice how this side's yards, that side's
I'll do the
feet.
yard thing.
I'd go yards to feet if I were you.
Yeah. Isn't the area of a circle and the circumference of a circle the same thing?
No. Definitely not.
It's always circumference is a